So it's interesting, a few years ago, Wim, who is part of on Semiconductor as well, asked me if at some point I might be interested in giving a talk like this, since I did have a background in test. And then earlier this year, Peter asked me if I'd like to give this presentation, and I was more than happy to agree to do it. But as I started thinking about, what do I have that I could talk to this group of people about? I haven't been to one of these conferences in, I think, 32 or 33 years. So it was in DC, and it was a long, long time ago. But I think part of the excitement that's going on right now in our industry is going on in test. And some of the speakers earlier have talked about machine learning, AI, and some of the things that I think that's going to bring to what we do as test professionals in getting and understanding that data. And so I want to talk about that a little bit and contrast it with what I call testing in the dark ages, which is when I was doing test development. I think a lot of us felt like this when we became test engineers. We were sort of the guy that did the tasting to see if what had come out just right was, I think the original test engineer was the test engineer in the dark ages. But it wasn't long after that we started trying to test components, and really our goal was just to select what are the good ones and what are the bad ones. Which ones can we sell to the customer? Which ones do we throw in the bin for recycling? And there was a little box like that had two green lights: functional test, DC test. And your primary goal, or frankly your only goal as a test engineer, was to get those two green lights to come on. And so, once you got those green lights, the parts went away. And I think that in today's world, once you get those green lights, that's when the real analysis of what happened in that test and what you can do with that data begins. And so while we had sort of the dark ages there, we have a real opportunity now going forward. But there are a lot of challenges that face test development engineers and test engineers today. We didn't imagine then the responsibility of developing a part and testing it and certifying it good for something like autonomous driving. A vehicle that was going to drive us, the closest possible thing maybe then was the moon launch rockets, or some of these things where you could test one part for 6 weeks and make sure it was suitable for the purpose, unlike today where you have to test a billion parts a week and make sure that they're at that quality level. Functional safety. Vehicles or other machines around us are going to make decisions on personal and human safety. It has to be validated. Digital medicine. A lot of the products that we build today, either implantable or they're in products that are helping people make decisions about their health. Again, those decisions are happening at a high enough value and a high enough volume level that we can't do the things that we used to do, which were really convenient and just test, maybe burn in and some other things. And then what I call digital dependency. Even the products that we used to consider consumer electronics, I can tell you people don't consider that anymore in their world. If your cell phone isn't working and you're using it as your GPS, or if you're using it in any number of other areas, but there have been studies where people's blood pressure actually goes up if their cell phone runs out of battery. And we're dependent on these electronic items nowadays. Even if they're products that we used to consider, maybe this is something where 300 or 400 ppm type of a problem would be okay. It's not okay anymore because it's the world that we live in. We depend on these things. Capacity optimization. As we continue to have to be more and more efficient, a lot of this is driven out of the test environment and things. Our yields, our factory and process improvements. How do we feed back the valuable information that we get into the front end of the process and make sure that our equipment is running optimally? Mass parallelism. As opposed to having one device under test, you've got 8, 16, 32 in parallel. The ATE vendors, the handler guys are working with us. We can do this over temperature now, but it creates a number of other opportunities and responsibilities. And then test temperature elimination. I think that's, we've sort of used temperature testing as, I won't say a crutch, but a bit of a crutch in validating how we do products. And I think we're going to get information, or I believe we have the information to eliminate that in a lot of cases today. Design methodology validation, I think that we've been doing that for a long time. Some of the papers that I saw that were being talked about were on this, but closing the loop between our simulation and device models, getting them back into the actual data that we're taking from our testers, figure of merit optimization for our products, and being able to make decisions on how we want to specify the products based upon the actual output and the data, whether or not they're going to be suitable for the purpose that we want them to be. And then product integrity. And product integrity, I think, is very different than zero defects, because this means that the product is the product. There's a lot of work that's going on right now in security and being able to make sure that the products are secure and unhackable. I saw that there's some papers on that this week. I think a big piece of that can happen in the test community, can happen while we have those devices under test. Die-level traceability is giving us the opportunity to really understand the data that we have. Anti-counterfeiting techniques, a big problem in our industry. Radiation hardening by design and validation of that are some more things that, again, all sort of fall in our lap that maybe in the past where if you just had a good one or a bad one, that was the end solution. So part of this is point learning. Part of this is what I call just, okay, we can set up a set of rules, they're static rules, and if we see something that's out of the ordinary, we call it out. So we've got good parts, bad parts. Is a pass really good? Sometimes that's a question. Is the one that we have that fails really bad? One of the examples of this that I remember from my very earliest days is we had done a analog ASIC, a custom part that was going into typewriters. And we could not mimic whatever noise situation was being created in the typewriter in the ATE environment. And we tested and tested and tested, and after months of work, we still got parts that didn't work in the typewriter that worked on the ATE. And we literally had a person sitting in front of a typewriter with a ZIF socket and a handler, and she would push good or bad, depending after she typed 2 words. We can't do that in today's environment with the volumes in the products that we have. And the other thing is, are we throwing away a lot of parts that are suitable, that are good for the purpose, and is that creating us some yield problems and some things that could go forward? We've seen some things looking at the data, just simple post-processing afterwards, and here's a case where 5 parts in a row had exactly the same output, same results. Well, certainly 5 parts in a row, as you know, there are no 5 parts in a row that have exactly the same outcome. So there's a problem that can be flagged. Those types of rules can be set up in your system. Here's a situation where we got a pass, bin 1 pass, after only completing about 8% of the test vectors, or 10% of the test vectors. Certainly those kinds of simple rules can be set up to flag those immediately as we go. But what about big data and being able to make decisions on data beyond setting up simple rules as we evaluate our products? Oops, sorry. There's a lot of discussion about all of the things that we can do with the cloud and all of the information that can be stored and gathered, and the amount of data that's being taken all the time now. My understanding is that on a jet engine, on one of the new jet turbine engines, there's about 1 terabyte of data that's taken every 20 minutes. Well, that's great, but a little bit like they were saying, what happens to the yellow cards when you're done with them? What happens to 1 terabyte of data every 20 minutes in operation? Are we really evaluating that data, making the kind of decisions on it that are there? The information is all there. Are we really looking at all of the information? And we have the same thing in our world in test. We've got information from the fab. We've got information from the device under test. We've got products that have come back from the factory, and we get a lot of data each time we do those things, but what are we doing with it? How do we manage that in a way that is going to continue to bring value to our customers, value to our shareholders? Well, we can reduce production costs, we can have a higher quality index, and then we can do a lot of data analytics through artificial intelligence. And I'm going to talk about just a couple of opportunities or a couple of cases that we have there. So what's the quality index of a part? Is a good part is the one where the lights come on green, right? Well, yes, sometimes, but we got it. But was it on the edge of a wafer? Is that the part that we really want? Is it how were the parts around it? Was it a good guy in a bad neighborhood? Has it been probed multiple times? Did it take 2 or 3 insertions to pass? What do we know about the part, and how good is good? Good guy in a bad neighborhood. Maybe you do or don't want to eat that strawberry. There's a strawberry in there. It doesn't have any problems at all, but if you look at the strawberries around it, you might think, this might not be one that I want to eat or that I want to feed to my children. And yet we have that situation sometimes on a wafer as we're doing probe. We'll sit there and there'll be 4 or 5 bad die and a good die in the middle. You can see a couple of examples on there where you say, gee, is that really a die that I want to send to my customer? Is there something that's going on this wafer in particular, something that happened here that I should know more about? Well, one of the things that we look at is, okay, how do we decide whether we've got a bad neighborhood? But again, all of this analysis is post-processed. After the bad guys have been inked, you go back and you can step across each of the die and you can say, how good is this die and how good are the die that are around this die? And this is all, again, just mathematical post-processing. You can go in and you'll get a different index or a different wellness factor for the die based upon the die that are around it. And here you can't probably read those from where you are, but there are a bunch of small sub-1 numbers for any of the die that could possibly be around a bad neighborhood based upon something that we call a kill threshold. And that says, what die do I not want to give to my customer, or do I not think is suitable for this purpose? And it's a pretty simple equation. There's die area and the sensitivity factor. And the question about a sensitivity factor is, how sensitive are you to having a part that is in a bad neighborhood? So here we sit here and we say, okay, there's a sensitivity factor of 10. This would cause us to ink out or to post-ink out those 5 or 6 red dye or yellow dye that are there in the heart of the bad neighborhood. And again, this was an example that we built. In reality, this whole wafer would likely be thrown away because of that yield pattern. But it was a really good demonstrator for what the power of this tool is. If you move the sensitivity down to a 9 in that formula, you can see now we've got about a 1% dropout. We throw away a few more yellow dye there. You can move down again. Now we're a little over a 1% dropout. But as you continue to increase this sensitivity factor, you can see that you step across, you begin to throw away a few more. Now we're up to 13% dye. Do we think that that's gotten all the bad ones? We can continue all the way till there are only a handful of good dye, depending upon that factor that we put in there for that kill ratio. This may be important, and it may not be a decision that you make right now. This may be a decision based upon e-test information, mechanical information that's come out of the fab. There are a number of other things that may help you set this sensitivity level. Maybe what are we going to put this in? Are we going to put this in the guidance system of the new A350 or the flight controller, or are we going to put this into a power bank that people are going to give away as a gift at the show? And so I think there's a lot of data, and again, but this is all post-processing. So this can be made based upon other big data that you pull into the system. Like I say, how close was this to the edge of the e-test data? How many times did we have to go through temperature in order to do this. And so you can sort of set that factor later and then continue to ink out any die that don't work. Another opportunity is to take a look at the actual physical buildup of the wafer in the fab and some of the metrology databases that are out there, and compare them with your probe data afterwards. In this metrology database today, it's almost impossible. If you look at where the gaps are here, we need more help from the EDA guys. We need more help from some of the machine tool guys so that we can pull these databases together and get a better view on this. If you look at the data here, this was just a test case that we did, but out of 41,000 parts, there were 530 defects found. But there were 33 die that were not detected at probe that had a visual defect that we probably don't want to ship to our customer. And those 33 die, those are the ones that get us. Those are the ones where the customer has a vehicle that doesn't start, or in a worst case scenario, you have to have an explant of a medical device that's implanted into somebody after a long time. So we really need to continue to work together so that these databases can be better correlated. See, we've got, right there's the fab inline inspection database, and then the wafer probe map. So it got most of them, but it didn't get all of them. If you look at the wafer probe, there's some there that showed up in the metal database that had scratches on that didn't get flagged at probe and can make it, they can slip through our systems. But big data allows us to do all of this correlation and comparison post-tester, so it doesn't slow down anything that we're doing on the test. But we do need some more help from the different EDA tool people in multiple disciplines so that we can get these databases to talk to one another. There's another example where parametric data on the fab tool says that this wafer would have had a shift. When we probe it, guess what? It looks a lot the same. Do we know that there's 100% correlation between our probe program and what the processing tool and the parametric data said? No, there's not 100% correlation, but these two databases, again, could be overlaid against one another and help us make some of those decisions. So, one of the challenges that we've had in our industry always is, do we test more or can we analyze more data? And in the past, we've had to find ways to test more and test more because we haven't had great post-processing capabilities. And I'm pretty sure you've all seen this picture before. The digital test engineer who gets his patterns, tests up in a day, and everything's running. The mixed signal or analog guy says, he's worked on it for 9 months and his test program is a piece of art. And I think we've all felt that way, and we've all probably been on both sides of that equation. But how do we get the mixed signal and the analog test to look more like the digital test? Structured digital is really well understood, and we've got great tools for it. We can do fault grading. We can go back and the analysis of what we find is extremely easy to correlate back. There are structured analog tests, but the vast majority of our analog tests still today is what we call functional analog tests, where we're just adding test after test after test to validate something that either our customer has said they're concerned about or something that we've found that we feel like we need to do to validate that particular product. So again, along the top line there, you can see we got 100% fault coverage or very close to it on all the digital tests. We do have some analog tests with very high fault coverage, and then we had some analog tests that have struggled with fault coverage. And so the challenge or one of the concerns that we have is how do we get those two sets of data to overlap a little better and look a little bit closer to one another. One of the things that we've done for a while now is dynamic part average testing. So we'll go out there and crank in the spec limits at probe based upon, again, the entire population of product, either on that wafer or the entire population of product in that boat of wafers, or maybe even based on the last 30 runs of that product that have come out of the fab. We can take a look at that data, we can slide the curves in, and we can say, okay, here's an outlier. We're going to take that out of the equation. That's going to help us find a defect that we wouldn't have found before. And this is a little bit what it looks like. You can see the final test limits are the far outside. There's static part average testing, and then the dynamic part average testing that varies back and forth. And if this was solving all of our problems, then we could stop the presentation right now. But here's a case, and this is a real case that we had in the company, where you can see that on May of 15, we had a part that was right at the edge, even with the dynamic part average testing. So the spec limit would have been the screen. The yellow part we already took out of the equation using our dynamic part average testing. But as you can see, we were still a long ways away from that with that part, and yet it shifted over time. You can see the little defect in the gate up in the upper right-hand corner. We didn't detect that part. Now, there's a lot of different things that you could do at that point, right? You could say, well, maybe we could use temperature testing, maybe we could do a voltage stress, maybe we could, come up with more and more things that would add to that time and those additional tests that we're putting in the functional testing to try and weed that guy out. But another solution is to take a look at the data that we've already got. So this guy earlier was just looking at the rise time on a certain set of pulses. When we took the rise time minus the fall time, guess what? It already showed us that peak. The data that we had already taken was telling us there was something different about that part in the distribution. When we took the rise time minus the fall time and set up a new set of dynamic part average testing based upon that set of conditions, the part would have been bad from the very beginning, and then it got worse. So, and you can see the spike in the data set. Those types of relationships between tests where we're doing dynamic testing are I think, the opportunity that we have with big data, because we should be able to crunch hundreds of variables. And again, this is all offline. This isn't on our test floor. It's not taking up UPHs and continuing to drive cost into our test. It's just giving us opportunities to find things that were already there, that we've already got the data that tells us we've got a bad part. We just haven't looked at the data in the right way yet. And I think there's a lot of opportunities. So with that kind of work, we can move some of this fault grading up, and we can make it much easier. It's still not automated. I think that there's some opportunities for some automation, and certainly we've worked with some of our EDA partners, mentors, helping us do this defect identification. They've been a great partner in that, and we've worked with them and others on the opportunities to see some of these defects. But again, closing the loop and getting that back into a more of an automated, more of a real-time solution with the test hardware. Still some work to do there. But if we can do that, it gives us an opportunity to get the analog structural testing to look more like the digital structural testing. And we can push that out. Those are usually products that take less and less time. We can eliminate redundant tests, and we can create a better use product at the end of the day. Increase our structured analog testing, and bring down some of the functional testing. I don't think we'll get away from it. I think there are things that either customers or use cases are going to deem that we still have to do some functional testing. But the more of it that we can reduce and the more of it we can put into a structured system and look at data that we already have, the better our end product is going to be. So how do we propagate this kind of learning through some more of the value chain? There are a number of things, and you've probably seen on here Optima Plus also a couple of times. Certainly another group that we've been able to work with and help us do this. But there's data in a number of different parts of our process, whether it's in the front-end fabs, whether it's in our test solutions, whether it's in our visual inspections, and being able to pull all of this data together and at the end of the day get a quality index for this product so that we could say, well, look, based on the probe data, based upon the fab information, we should be very cautious about this wafer, or this is a great wafer. It represents the population of products that we have, and we can use very simple data post-processing going forward. But there are a lot of inputs, the other thing is looking at the back end and test. And again, one of the things that we're as concerned about as getting the right parts and the highest reliability parts to our customers, being able to do it in the most economical fashion possible. This is just a set of inputs where we can pull data that gives us indications of UPH losses. So we're starting to lose UPH and act on that. But as again, you can see jam rate monitors, test OI controls, there's a whole host of things that we need to be pulling data down from, using that data to try and point us back to a root cause solution on something. So at the end of the day, what we really think is that the product will should have a report card. Was it in a bad neighborhood? Was it statistically in line with what's going on? Is it a yield position where, even if there's a 40%, 50%, 60% yield on a product, if every other wafer is at 96%, that's a product that we really don't want in our population. It's a strawberry that I don't want to eat. And I think that by using big data at a number of different input points in our process, we can get that scoring and we can get that learning. We talk about artificial intelligence, but it's really a two-edged sword. Because I think our input to this, we've got the highest value today that we've ever had as test engineers. We own the data, and artificial intelligence doesn't exist without data. You have to be able to, and we're right at the front end of the data acquisition. So, I think that, there was that kind of cartoon in the beginning that talked about the guy that was tasting the wine for the king. Where we're at today would be more like Robert Parker tasting the wine. And, if we tell somebody it's good, if Robert Parker tells somebody a wine is a 98, the value of that wine goes up significantly. I think as a test community today, if we tell somebody a product is a 98, the value of that product goes up significantly. And I think we'll be able to extract value for that, which is a position that I think is a very enviable position for us to be in test. I think we can add the value. We can make the fabs run more efficiently. We can make the designs come out cleaner, and we can ensure that the customers are getting product that meets their requirements. The other side of that, though, is if we give them bad data, we're going to have bad intelligence. Artificial intelligence is only as good as the data that feeds into it. And so, there is a responsibility for us as a test community to make sure that what we're feeding into that AI machine isn't scrapping hundreds of wafers that don't have a problem, or isn't letting hundreds of wafers through that potentially do have a problem. Because I think that as we use the data, machine learning to go forward, we do have the opportunity, if we feed bad data into it, that we're going to get a lot of bad data out of it. So rather than having a part or two that might escape, we might have entire boats if we're feeding the wrong kind of information or not enough information into the AI decisions that are going to happen going forward. So that's really what I wanted to talk to you about this morning. I appreciate the chance. It's been a long time since I was a test engineer, like I said, but I don't think, I think if I were a test engineer now, I'd be a lot more excited about it than I was back then, because I really do think that this is where the data comes from. And if we don't have good data, we've got problems, but if we do have good data, we have an opportunity to change the industry. So thank you.